Colloquium. So today we are very happy to have Professor Mustafa Amin from Rice University. Mustafa did his PhD from Stanford University. Then he was a Pappalardo Fellow at MIT, and then a Gaudy Fellow at University of Cambridge. And then he joined Rice in 2015. So Mustafa has done some great work on early universal cosmology, pioneering work on early universal cosmology early on, and nowadays he's mostly focusing on light dark matter, and he's leading the charge on how to discover wave like dark matter. We'll be talking about.
Thanks a lot, Ranjan. It's been really spectacular. I've been in Bangalore now for a week, talked to a lot of you, and I especially want to thank the students and postdocs. I've had great conversation with you all yesterday and hope to continue that today after the colloquium. For those who haven't been able to contact, it will be in E106 after the colloquium, so we'll meet there afterwards. And thanks, Ranjan, again for helping organize everything, and Rajiv as well for taking care of me a day before. And so it's a pleasure to be here. And let me start by telling you what I want to tell you about, which is I want to tell you about dark matter that's very light. And as you'll see, spin will play a role in this as we go on. To set the stage, I'm sure you have heard this before, but we have ample evidence now that a large fraction of the non-relativistic matter in our cosmos seems to be not so interested in interacting with us, right? It's at least non-gravitationally. Most of the evidence we have is through its gravitational interactions, and it makes up a majority of the non-relativistic matter in our universe. A bit of history about this. I'll be quick through this. Arguably, the discovery of dark matter came about with Fred Zwicky when he noticed that in the Coma cluster, galaxies were moving about a bit too fast in comparison to the matter that you could see. So he was applying Newton's law to figure out how fast things should move, and they were moving way too fast compared to the matter you could see. Fast forward a few decades, and in the 1970s, Vera Rubin and Ford and others, now looking at smaller scales inside galaxies, they found that stuff inside galaxies was moving too fast compared to the visible matter that you could see. Again, applying Newton's laws, you could infer that there's some more matter there that you couldn't see. Fast forward again to pretty much the modern day. What you find here, this spectacular image of the light from the time of first atoms. Right? This is the cosmic microwave background. More specifically, these are, after you take away the average, this is an anisotropy in the cosmic microwave background. And this image is from the Planck satellite. It turns out that this image provides us one of the strongest evidence for this unseen matter. And to just give you some intuition about this, here is a patch of that map. This is what we observe right now, this anisotropies in the cosmic microwave background. Now imagine that if we were living in a universe where everything else was the same, but there was no dark matter, then we would have seen this sort of an image. Even by eye, you can see that there is a difference between the two, and this provides evidence. Again, you have to do a little bit more work to be absolutely sure that there should be this unseen dark matter that doesn't interact with regular matter or standard model matter by any other means than gravitation. Yes, please.
Pinpoint this difference what you have shown. Is it requiring indeed explicitly dark matter or even modifying gravity which is mimicking dark matter? How do we do something?
It is quite difficult. In fact, I know of many efforts to fully reproduce the cosmic microwave background using modified gravity. So far, there's been one paper that somewhat achieves this over many, many years. However, even there, you are forced, the modified gravity has multiple fields that you have to introduce.
I mean, basically, bond is
No.
replacement of people.
No,
Communication.
that cannot reproduce this. Absolutely not. You have to work hard. You have to have a modified theory which has multiple additional fields, scalars and so on, and vectors as well. And if you arrange it just right, it can do this, but even that is hard, not in detail. Okay? So I would say just for MOND, no, you can't do this. Yes? Yes. So the reason is that we see a certain, to get from the structure we see at that time to what we see today, if there was no dark matter, we wouldn't be able to grow that much. Okay, so dark matter provides this assistance. One way of saying this is that dark matter was already clustering when atoms could not cluster because they were strongly talking to photons. So they already were clustered at that time. And as soon as the atoms were able to cluster, which happened when they stopped the electrons and protons combined together and they stopped interacting with photons, these baryons or atoms just fell into the potential wells that already existed. So dark matter was providing assistance to explain the picture. So that's why this image arises. Okay, great, thanks, and please continue to ask questions as we go through. You take these initial conditions at the time of the first atoms, and you allow for only gravitational interactions. You put it in a large computer with just gravity, and you ask, what should dark matter do? And this is a kind of filamentous structure with nodes and filaments that arise from these simulations. Here is sort of just another visualization of that. The black things there are the dark matter, which of course we can't see. With some additional work, including astrophysics, you can figure out where baryons should be in this picture. And the bright images, they're painted on here. They're not part of the simulation, at least this one. You can see that most of the clusters and galaxies and so on are located at the nodes of these filaments or within the filaments themselves. So this is how dark matter is distributed, and it provides some scaffolding within which baryonic matter or regular matter that you and I are made up of resides. This was sort of a qualitative picture of this clustering. We have measured the clustering of galaxies quite precisely now with surveys, for example, like the Sloan Digital Sky Survey. And then when you plot how clumpy is dark matter as a function of length scale, you have a prediction from dark matter, or rather matter as a function of length scale. That's this gray curve. And then you put on your data, and it matches pretty well, at least on these large length scales, which are on the scale of millions of light years and above. So this tells you that at least on large length scales, this picture of there being dark matter, just interacting gravitationally with no other properties required, fits the data pretty well. So once again, just summarizing, I have only given you a few bits of evidence. There's a lot more. We have evidence that a large fraction of matter in the cosmos is dark. It doesn't interact with standard model apart from gravitation. What is missing in this picture is we don't actually know the microscopic identity of this dark matter. We know it interacts gravitationally, but other than that, we don't know what its mass of the particle is, what the charge is, what its interactions are, what its spin is. And as you can see from the images there, apologies for images I stole from the web, other people in the audience. Ranjan looking like a boss, with his glasses on. So these people, of course, you can talk to them about, they have been engaged extensively in trying to really fill up this picture of what dark matter really is. So I'll give you an overview of what we know so far, and then move on to things that I hope to learn in the future. So let's start with what we know about charge. From astrophysical observations, the electrical charge of dark matter, we don't know what the charge is. As you'll see, for all the properties, I'll give bounds, right? Because we don't know the identity of the particle. We know that the charge of this dark matter particle, the electric charge, has to be at least smaller than a millionth of an electron charge. This comes, again, one way of getting to this is through observations of the cosmic microwave background. Okay, I told you that to get this picture to work, dark matter shouldn't interact very strongly with baryons. If you give it charge, it's going to interact with light. So this is one of the ways in which you get a constraint. We've also tried very hard to detect, again, the interaction of dark matter with regular matter. We haven't seen this through terrestrial observations as well as astrophysical ones. That gives a bound on this interaction cross-section. Again, it's quite small. Spin, we haven't discovered it, so it could be a boson or it could be a fermion. We don't know that yet. And then what about particle mass? That seems like something we should know, right? It's dark matter affects us through its mass. We should know something about it. And that situation is in particular somewhat embarrassing. Okay? The mass of the dark matter particle currently, if it's a fundamental particle, can be anywhere between 10 to the minus 19 eV to 10 to the 19 GeV. For comparison, remember that an electron is about a mega electron volt. Right? So this is can be much lighter than that, way heavier than that. And if you allow dark matter to be a composite object, it can even be up to a few solar masses. So perhaps for the students amongst you, right, you might ask, why such a broad range? Why am I allowed to do this even? And the reason is, again, that all we know about dark matter comes from its gravitational interactions. Gravity cares about mass density. Okay? And you can construct the mass density with the mass of the particle times the number density. The mass density, for example, in a local neighborhood, we know pretty well. But you could construct that mass density by making the mass very small and the number density very big. Or you can make the mass very big and the number density very small. So that's why you can have this wide range, because we only know the mass density. So what is the domain that I mentioned? This domain that's constrained right now from observationally is that the mass of the particle has to be heavier than 10 to the minus 19 eV. And on the other end is a few solar masses. Again, at that end, it's composite. It could be also be primordial black holes in that area over there. Many, many kind of exotic things could be hiding there. In an interesting way, you can see that both of these constraints come from looking at the, give me one moment, looking at the velocity dispersion of stars in systems. And what you find is that if you had additional substructure, then it would jiggle the stars dynamically a bit too much, and we don't see that, and that's what gives these bounds. Another way of getting the smaller bound is something I talked about recently. Some of you were there in the talk at RRI about this comes from production mechanisms and initial conditions. That also gives you a bound there. Yes, please.
So can you maybe you remember what is the experimental limitation of the mass of the photon?
So it's comparable to this. Okay, it's comparable. It's a bit better than here. And I actually usually when I forgot to mention it today, it is somewhat interesting, that we are talking about particle masses which are supposed to provide most of the non-relativistic mass, and its mass is not too far away. It's within a few orders of magnitude of the bounds we have on the photon mass. I think from Jupiter magnetic fields it was 10 to the minus 17 or something, but then we have better ones that go beyond this. That stronger limits, right? So that's right. Do you remember what the number was by any chance? 30? Okay. 30? Oh, it's even 31. Sorry. So I was wrong about that. So it's even much better than this, right? Much better than this. Yeah, I remember the Jupiter number, not the CMB number. Yeah. Okay. Thanks. Yes. So if dark matter is lighter than this and it makes up all of the dark matter, then yes. Right? So fraction, exactly. I mean, people argue about this because still, but I would, from my understanding, with Dalal and Kravtsov, there are very few assumptions in there. So they're looking at ultra-faint dwarf galaxies, and they look at the motion. They're trying to figure out whether there's extra velocity dispersion of the stars there. It's a pretty clean system, and they don't find it there. So that's where the bound comes from. Again, from things like Lyman alpha and so on, the bound is sitting more closer to 10 to the minus 21 eV. So this is stronger than that. So different people take different ones to be more, and if they want to work on it, they will allow for more range. Yeah. Yes, only gravitational. So the bounds get stronger, right? But here I have assumed, sorry, actually I don't know in which sense the bound gets stronger. So in this case, the bound I'm describing comes from free streaming of dark matter. So that is assuming that dark matter can move freely, right? So if you include interactions, then free streaming will be reduced. So in that sense, the bound will be weaker, right? So because it will interact more, it can't travel as far, right? So in that sense, it will get weaker. So the free streaming effect is not as important anymore. Okay. So let me, still this range is broad. So how can this range be narrowed? Of course, it's not that nothing is known. If you be completely model independent, the previous slide is what I can say, we know. But as soon as you try to include some assumptions, you will quickly narrow this range down. Let me give you a quick example. So as you know, whenever we think of fundamental particles, we think of them as bosons or fermions. Fermions have the important property that they don't like to cluster, right? They don't like to hang around together because of Pauli exclusion. Bosons have no such qualms. They like to sit on top of each other quite easily. So if you make the assumption that the dark matter particle is a fermion, then you immediately get that from 10 to the minus 19 eV, the mass bound goes to 100 eV. That's a huge jump. Okay? Why is this happening? The reason is that if you try to make up the same mass density with the help of some mass and number density, as we argued before, if you try to make the mass too low, the number density goes up. If the number density goes up, then these particles with a given de Broglie length have to sit close to each other. Pauli exclusion prevents this from happening, and that's where the bound is coming from. Okay? A more detailed one is available with phase-space arguments and so on, but this is roughly essentially the idea. So again, this range is cut significantly if you include some assumptions. If you now make additional assumptions, for example, that dark matter is thermally produced, then it will go to a kilo electron volt. So as you add assumptions, you can narrow this range significantly. However, going back to the case of bosons instead of fermions, this bound goes away. Indeed, now if you go to light mass regime, okay, so masses below an electron volt, you will find that if you again do this number density argument, you will find that these particles, de Broglie wavelength is such, they essentially sit on top of each other. Okay, so they are not separate particles anymore. And as you keep on reducing the mass, they sit so much on top of each other that it's not really sensible to think of individual particles here. It becomes sort of a Bose-Einstein condensate. There are so many of them sitting on top of each other. Right? And so effectively, it starts behaving, as with BECs in mean field theory, it starts behaving like a classical field. So you can stop thinking of these as point particles and start thinking of this as a field. So this aspect of this, for me, has been particularly interesting. Why? Because as soon as you go into this regime, a lot of interesting dynamics, including things like wave interference, linear and nonlinear wave dynamics, formation of solitons and so on, all of these phenomenology comes into play in the context of dark matter. And this type of things have already been, of course, explored in the context of early universe cosmology, where I sort of more or less started thinking about this. But it has also played a significant role, in fact, in condensed matter systems or cold atom systems, including Bose-Einstein condensates. Okay? So a lot of these things that I will talk about, for people who work on those fields, you will see some parallels to that in the talk. And towards the end, I'll also tell you about some efforts that we are making at Rice to connect these parts as well. Okay, so just a sense of numbers. Now we are bosonic fields, and we are looking at things in the light regime that is much lesser in EV. If you look at the occupation number per phase space volume, the numbers that you come out with are things are really large. Okay, 10 to the 23, 10 to the 83, so it's clearly so high that it's sensible to think about these as fields. Interestingly, the wave dynamical scale, or the de Broglie wavelength, starts becoming, at these masses, starts becoming macroscopic or even astronomical in size. Right? So it can be meters or even parsecs in size. So these effects of the wave dynamics, you should be able to probe for such light masses on astrophysical scales. And that's the part that got me really excited, and what I'm going to be talking about is related to these phenomena. To whet your appetite a little bit, here is a cosmological simulation of vanilla CDM, cold dark matter, without thinking about its wave dynamical effects. So this is heavy dark matter. This is a dark matter only simulation with adding gas and stars and so on. And that's sort of a zoom in to look at some distribution inside one of the filaments that is being shown here. If you take very light dark matter, 10 to the minus 21 EV-ish, right? And in the same scales, the simulations would show, and also analytically you will find, that the description would be very different. These fringy effects that you're seeing is basically because of wave interference. Okay, so you can start seeing this, and this also has some impact on the distribution of baryons and so on, so people are trying to probe this to understand the nature of the dark matter. So clearly there are distinctions to be seen when you go to light masses, and it's worth probing. If we see some of these effects, we'll understand. It's giving us a new handle to understand something about the mass, at least in this case, of dark matter. Yes?
What sort of equations do they say?
Give me 3 slides and we'll get there. Right.
And what is the rightmost panel?
So rightmost panel is just a zoom in of this region in the simulation. It's some cluster scale region, right? And it's a density of dark matter. The color is just a density of dark matter. Right? So the brightest regions are more dense. The darkest regions are less dense. And the important difference is just these interference fringes that you see. Because it's waves, they interfere with each other. So some regions, the wave interference leads to 0 density. Some regions, it enhances it. That's what you are seeing there. And something that you wouldn't see with particle dark matter, with heavy dark matter rather.
So that if this is a massive, let's say dark matter, really massive, then the wave thickness is going to be
Yeah.
in that case it will be particle.
Yeah. Yeah, exactly. I think the way to think about it is the wave dynamical effects appear on the de Broglie scale, which is h bar over mv. If the mass is big, the scale gets very tiny, so you can forget about the wave dynamical effects. Right? The velocity dispersion is usually set by gravity, so that you don't get to play with. The only thing you get to play with is the mass. So as you keep on increasing the mass, all the wave dynamical effects essentially become unimportant.
So if I understand correctly, so you are basically making certain ansatz about the properties of this dark matter, basically simulating and seeing what comes out.
Absolutely. Yes, right. And see, and yeah.
What do you plan to do, like what do you want to write on?
So we would like to, so suppose we go and look for this distribution of density, say with the help of regular matter, because it will be affected by this, right? How stars and galaxies are distributed, as well as, say, you do something like gravitational lensing, and you're trying to see if you can see these types of density variations. If you see them, then you will have an indication that the dark matter particle is very light. So it'll give you a bound, not a bound, but actually a detection on the mass if you actually see this. Right? If you don't see it, you will keep on bounding the mass of the dark matter. Right? So far, we've put bounds on the mass. We haven't seen these effects. But the reason is, to me, it's exciting, as I will show through the rest of the talk, is there are many such things we can look for observationally. And we'll see that all of them, especially when we go to small length scales, are quite promising in hopefully detecting them, but detecting the mass of dark matter or the spin, but if not, at least putting a strong bound on it. Yes, please.
So you made an argument using Bose-Einstein property of
Yeah.
spin integer
Right.
particles to argue that dark matter particles can come much closer together than they were earlier. So the model that you have for this fluid of dark matter, is it a quantum fluid that you have in mind, or is it a classical fluid that you have in mind?
So
You're
it's
using Bose-Einstein property, which is operative, so to speak, only deep inside the quantum.
this is a subtle. It's a long answer I would have to give in sense of what I would. So I will punt for the moment, and we can have a longer discussion. I think it's at the end of the day, it's a classical field, okay? Because occupation number is so high, but it is. If you think about, I can set it up as a quantum mechanical problem, and you will see that this is. The description is precisely as you would describe a BEC. There are issues where you can think about, okay, the coherence of this, how was this set up, and so on, that make it a little bit tricky. The reason I say it's classical is that the fluctuations above the mean field theory will be small. So it's a quantum system, but the fluctuations about mean field, because occupation number is so high, is essentially negligible. So treating it as a classical field is absolutely okay. So I don't need to worry about those effects. And you'll see that even if you, suppose we don't live in a world without quantum mechanics, of course, but if you were to even just write down wave equations, you will get the same behavior automatically.
If you thought of it as BEC, then there would be phenomena that could happen which are visually difficult or impossible for them to happen in an ordinary fluid.
I think, as you will see, the equations describing this are precisely the mean field equations of a BEC. Okay, so it's a Gross-Patayevsky equation. Right? So you will find that all the things you get in mean field theory happen here. The things that if you go beyond mean field theory, I won't be able to describe it here. These are great questions. Let me now jump into a bit more. Already questions have been asked is, what are you going to do with this? Right? How are you going to probe this? So I'm going to talk about 3 distinct areas. One is about interference of waves and how this can provide a probe. Then I will talk about growth of structure, how structure grows somewhat differently in this case, both in the context of initial conditions and at late times. Unfortunately, somewhat with a heavy heart, I'll say that I won't focus too much on the initial conditions because otherwise the talk will be too long. But ask me afterwards about that. I will also talk about some fascinating objects close to my heart called solitons that appear in these things. And they provide an additional handle in trying to understand. If we try to detect these things, they'll provide an additional handle on understanding the properties of dark matter. So these are the 3 things I'll discuss before summarizing at the end. For the theorists among you, I should first just write down something so it's clear what I'm talking about. So far, I've just been talking in words and pictures. Here is, so if you think of dark matter as a scalar field, that is a spin 0 field, it's described by the action written above. It's just a simple Klein-Gordon field with massive Klein-Gordon field with gravity. Because you could go ahead and work with that, which is perfectly fine. But if you want to really do simulations or you want to understand it a bit more easily, because it's dark matter, it's non-relativistic, and this really makes your life a lot easier. What you can do now is you can take your relativistic field and break it up into fast and slow modes. Fast modes are things where things vary on the Compton scale, slow things where things vary on a much larger length and time scale. And you can separate those scales out. And you can, if it's non-relativistic, you only have to worry really about the slow time scales. So what we do is we take the relativistic field and break it up into 2 parts, a slow part and a fast part. And then we write down the equations for the slow part because the fast part, which is the Compton part, just comes along for the ride. So the equations for the slow part, the psi field, as you will see, it just satisfies a Schrodinger-like equation. In fact, it's exactly that equation, if you're familiar, except that there is now a potential here. Instead of an external potential, in this case, this is a gravitational potential, which satisfies Poisson's equation. So this equation we are familiar with, and this is what we solve to understand what's going on. This is for scalars. It's not too difficult to now extend it to higher spin fields. So if you look at vectors, it looks like electromagnetism. This is a field strength tensor with a mass. This mass could be put in by hand, or it could be related to a dark Higgs, and then with gravity. Again, here you do this split between the fast modes and the slow modes. The difference is now this is a 3-component object, so this psi is also a 3-component object. Okay, so it's, and then again, you can write down the non-relativistic equations. And the nice thing is that whether you deal with scalars, vectors, tensors, as soon as you go to the non-relativistic limit with just gravity, the equations are always the same. All that's happening is what used to be a single component object here now becomes 3 or 5-component object. Okay? So this is quite nice, and we were quite happy when we saw this because it really makes life easier to explore many different spin things all at once with the same framework. Good. Sorry, so in effort to simplify, I have removed the, so there will be a Hubble term here as well, first of all, right? The covariant derivative part introduces a Hubble term, so we of course include that, and there is expansion in here as well. I'm just writing down the simplest version. In the simulations I'm showing, and everything is included. It's a non-relativistic limit, so effectively what you're doing is you are having a expanding background, and you do effectively Newtonian gravity in an expanding background. That's what these systems are doing. And as I'll show you later, we have done the checks with fully relativistic things to check that they're consistent in the domain where they overlap. So the number of components, by the way, of this object psi here is basically 2s plus 1, where s is a spin. So 0, it's 1 component. Spin 1 is 3 components. Spin 2, it's 5 components. This is simple here. When you add self-interactions, there will be additional terms along with this here. For people familiar with it, this will be the nonlinear Schrodinger equation with extra interactions there. That also can be done, but for most of the talk, I'll ignore that for simplicity. As always, before I show you some results, we should talk about the conserved quantities in the system. The particle number is conserved, the energy is conserved, angular momentum is conserved, as you should expect. These are the expressions for it. What I want you to pay attention to is the last two things here. These are both angular momentum. This is the orbital angular momentum, and this is the spin angular momentum. In a relativistic theory, a sum of these two is conserved. In a non-relativistic theory, it turns out both of these are independently conserved. And if psi was a scalar, this cross product has no meaning, so spin angular momentum is 0, as it should be. It's only when you get higher spin fields when this becomes active. Just to emphasize, because this will show up again, so the spin angular momentum is, I've introduced H bars and such again, is just a cross product of this field with its effectively the time derivative, but because in the Schrodinger picture it's just the dagger of that. And this quantity will be bounded by between 0 and h bar times n, where n is the number of constituents that you have in the system. Here is a little movie where I show you where, scalar fields, it's simple, it's just oscillating in time and doing nothing else everywhere. For a vector, it's a little bit more interesting. For a vector field, the arrows that you are seeing are the field themselves, the vector field itself. This is the x part right here, the truly relativistic field. It's rotating with the Compton frequency. You see this going around. So this is what dark matter field is doing at each point in space. You notice that these ellipses that is going around in are slowly changing. The slow change is related to the slow part. The oscillation is related to the fast part. As you're familiar with light, when you have something that's elliptically polarized, it has angular momentum. So that's where the spin angular momentum here is coming from. Okay? So because these are generically, they will not be linearly polarized everywhere. And you'll have spin angular momentum in the system. And as you work through it, you will find that as things cluster gravitationally, spin angular momentum also gets clustered significantly. And it can have, as I'll show you, it'll have some effects. Okay. So let's now dive into this phenomenology and see where we end up. I told you that interference is important, and I've already shown you examples of it. Let me try to use interference to tell you how we can distinguish between scalar and vector dark matter. If you take one of the key properties of waves is that they interfere. You add two waves, and you find that square of the sum is not the sum of the squares. Right? That's what interference means. For scalars, if you add them, you have to interfere. There's no option. For vectors, you could put one wave in this direction, one wave in this direction, and you don't have to interfere. They're independent of each other. So you notice that interference effects, when you have vectors, can be reduced. Here is an example of the density, which is the square of the sums of waves. In the scalar case is the blue one, which has large excursions away from the mean. In the vector case, the excursions are weaker. I don't know if you can see this very clearly, but this is a picture where I've just superposed many waves. It's what you would see inside a halo of dark matter. And here, this is the color is supposed to be density. You notice that the density contrast here is higher compared to the other images. This is a scalar case, that's a vector case, that's a tensor case. It's because interference effects are reduced as you go to higher spin fields. And they're reduced in this way. It's just 1 over square root of the number of components. Here is a simulation of one is a scalar case, one is a vector case. If you want, you can try to guess which one is which. It doesn't look too different at the moment. But you'll start seeing differences between the two if the projector is allowing it for the moment. Anybody want to take a guess which one is a scalar? Right. So left one, right? Because there's no interference effect, more interference effects. And that's what I was trying to. So this is a dynamical realization of what I was saying before. So again, you can probe these things, as I'll show, these interference patterns, which are genuine density fluctuations, with the help of observation. Yes, please.
So this Kraftstoff and wait, sorry, this is a bit technical.
Yeah.
This Kraftstoff and Dalal paper uses this interference to each of the stars, right?
Yes.
Then that limit should be different for vector data because they sort of talk about they don't talk about the spin, but then this definitely changes the medium.
Clearly, you seem like a plant from me because give me 2 slides, and I'll describe exactly Kraftstoff result and the context of spin. Okay. Sir, there's another question. Yes.
Maybe I'm completely misunderstanding, but as far as I understand, these interference patterns are in the scale of clusters.
Not necessarily. It depends on the mass of the particle.
Yeah, but could you,
Yeah.
you know, a few slides ago you showed that the dark matter field at each point, the phase behaves independently. But for interference patterns at large scales, there should be some coherence, you know, between the phases at each point. So how is that happening?
So if you look carefully at this picture, these were the locations of the arrows, but notice this color, which I didn't talk about. This is a scale of coherence. So I'm only showing you samples between different coherence regions. If I was to actually plot all the arrows, you will see coherence on the de Broglie scale. Okay? So you will see exactly what you are expecting, that there is a length scale over which all of these things will be roughly coherent with each other. They're slowly varying. And then after that scale, it'll be some other pattern over there.
How is this coherence set up?
So essentially, that's a great question. So it's initial conditions, right? So it's initial conditions. The way you produce a field, you will already produce it with some level of coherence. But it's not the same that you see here. This level of coherence then gets gravitationally processed because you cluster and so on. And essentially, the coherence length is just 1 over mv, where m is the mass of the particle and v is the velocity dispersion. That's what the coherence region ends up being. Okay? The time scale is 1 over mv squared. The length scale is 1 over mv, with h bars included. Sorry?
We have non-Gaussian, so we don't have one by
I think on these small length scales, it will not change because these are locally produced fluctuations. If you're looking on very large length scales, these interference patterns are not so important. So if you're asking about primordial non-Gaussianity, it's unlikely to play a role in this case because those I'm imagining on very large length scales. Okay, where was I? Yeah. So we already saw the movie for this. This is scalar dark matter where I did the simulation. This is the vector case, and you can see difference at the end. These interference patterns that Ranjan just asked about have been used by Dalal and Kraftstoff, right, to put a bound on the mass of the dark matter particle. Very quickly, if you just go through this calculation again, using this fact that's where it's the 1 over square root of 2s plus 1 suppression interference patterns, you will find that the mass bound is just affected by this factor in front, where s is the spin per boson of the particle. So you notice a factor of 1/3, so it's really a weak dependence. So it's an order unity difference. So it won't change this bound by any significant amount. Nevertheless, the nice thing is now that they have done this analysis for a scalar and what we showed how it scales with spin, you know the answer. For those who are not aware of this, what Dalal and Kraftstoff did was they were looking at I guess I already said this, but ultra-faint dwarf galaxies. They were looking at the smooth distribution that one should expect based on the light of dark matter, and also then they were looking for fluctuations beyond the smooth distribution. And what they found was there was no real evidence for extra fluctuations there, and that's what they use to put a bound.
This fluctuation is in
Density.
what observable?
So this picture is in density, which corresponds to gravitational potential fluctuations. What they were looking at was as stars were moving around orbits, whether the velocity dispersion is increased because of these fluctuations. So because they're passing through these gravitational potential wells, they'll get a bit kicked around. So the velocity dispersions of stars, if these fluctuations are there, should increase. And they didn't see it, so that's how they found the bound. This was also been done for the Milky Way by looking at how puffy our disk gets because of these effects. And again, we don't see a significant effect, so they put a bound on the mass. In that case, the bound is weaker. It's 10 to the minus 21 eV. Here, this is the strongest one that I know. And people are actively trying to improve on this even further by taking into account what is happening in the core, which I'll mention a little bit later. Here is another example of how you could probe these interference patterns. You could do this with the help of gravitational lensing. So you're looking at some jet from a faraway quasar. If there is no interference in the middle, you should see a nice, clean image in principle. If there are these interference density fluctuations in the middle, that nice, clean image will get a bit wobbly. We don't see the wobbliness in these images, and that puts a bound again on the interference patterns, and that's what's written right here. So again, another way of putting a bound on these masses. And if you include spin effects, it just comes with some factor 2s plus 1. If one thing you take away, all the observables that people have done for scalars will be scaled in some power of 2s plus 1. Okay, so it's an easy thing to remember in this case. Oops. Okay. You can also go deep inside the halos, and you can see that for vectors and scalars, you will find difference in the inner structures of halos. I can tell you a lot more. The shapes are changed a little bit, and the density at the center, given the identical initial conditions. There's also something we can look for, although it's not so clear how to do this carefully, because of course in these simulations I haven't taken into account baryonic effects and so on. So I would take this with a grain of salt at the moment. Okay, let's now go. This was sort of just interference. Let me now go to growth of structure. I'll have to speed up a bit. Sorry? Okay. How much time do I have? 10? Oh, okay. That's a lot. Okay. Hopefully I'll be able to get through. Okay. Let me, as I said, I won't talk about the structure formation in the early universe in this talk. Let me just focus on some small scale structure and how it grows there, because I think it's fun to look at it. This work, by the way, is led by Mudit Jain, who was a postdoc at Rice, and two of fantastic Rice undergraduates, Visha and Jonathan. They are the ones who did these simulations. You are seeing what I showed you before. Here is a patch of dark matter inside a halo. These are the density fluctuations that we begin with. They basically have no features. The Maxwell-Boltzmann distributed waves. This is spin 0, spin 1, spin 2. I just let this evolve under the influence of gravity. And let's see what happens. So now all I'm doing is solving the Schrodinger-Poisson system for scalars, vectors, and tensors. So you notice that very quickly, well, long time in cosmological terms, but quickly in these simulations, you see this dense structure emerge. There's a blob that's emerging there. And if you probe inside it, it will be coherent in its phase there. And I'll have a lot more to say about that. You notice that similar thing seems to be happening in the vector case, but it's taking a while. And it's taking a bit longer, but it also emerges there. So same thing is happening for the vector case. And if you wait even longer, you're probably seeing it already, same feature is also appearing in the tensor case. So the same phenomena seems to be happening in each case, but they're delayed, one compared to the other. What you're seeing is effectively, if you think in terms of classical physics, just wave dynamics, you're seeing interference allowing for chance effects for many waves to come together and form a localized object. You can also think about it, if you want, in terms of Bose condensation. This is just Bose condensation coming about. You can calculate what the time scale of the emergence is, and it precisely follows the number of components. If for scalars it is something, for vectors it will be 3 times as longer, for tensors it's 5 times as long. Okay. So that's the lesson you can take away from this. You can actually calculate the time scale by just thinking about gravitational interactions of these things, and it turns out to be pretty bang on target. Even a simple estimate, at least on log scale, it turns out to be correct. Usually you think of interactions as being n sigma v, right? That's the interaction rate. There's an extra factor n, which is basically the occupation number per de Broglie volume. That's your Bose enhancement factor. So because these are bosons and they're highly occupied fields, you increase the interaction rate significantly, and that's what's causing this phenomena to happen. So if you didn't have this large occupation number that you were talking about, something like this would not be visible in this case. You can also, for those of you who love Boltzmann equations, you can go through this and predict how long it will take for these things to emerge a little bit more carefully with different masses and so on. And again, credit goes to Mudit for working through this carefully. What are these blobs that you were seeing in here? These blobs that you are seeing are solitons. What are solitons? Well, they are long-lived dynamical excitations of the field that basically hang around by themselves and don't like to disperse away. The discovery of solitons, it's a fascinating story that I was telling some of the students yesterday. John Scott Russell, apparently in 1834, was riding around a canal in Edinburgh, and as he was riding around, a boat came to a stop in this canal, and it created a pulse in the surface of the water. And what he saw was that this pulse, instead of dissipating away, held its shape and kept on propagating. He writes that he kept on following this on horseback for almost 2 miles until it disappeared into the woods, and it had not lost its shape. So this was the discovery of a soliton, in this case in fluids. Here, by the way, is a recreation of that soliton more recently in the same canal in Edinburgh. Now, this is, of course, a effectively 1D system. We are talking about 3-dimensional ones. But these solitons have now been discovered experimentally and verified in optics, hydrodynamics, Bose-Einstein condensates, and they've been used in many different contexts. Unfortunately, for my field of high-energy particle physics and cosmology, even though we have been talking about this for now decades, we've never seen evidence for it. I hope it changes soon. These solitons, by the way, are a special class of solitons called non-topological solitons, meaning they have nothing in topology that's preserving them. It's just stable because of dynamics. Inside a soliton, the field is just oscillating. People have worked on this a lot, including myself, about the stability and so on. If gravity is holding them together, they're called scalar stars. If self-interaction is holding them together, they're called oscillons. And now, more recently, we have been working on extending this to higher spin cases as well and seeing the same phenomena. You can find solutions for this, at least the non-relativistic aspects of this, by just solving for a stationary state. You can even get this by just saying, if I have a fixed number of particles, what is the minimum energy configuration? And these are the objects that you get. In the case of vectors, something truly fascinating happens here. Okay? These solitons are localized objects, but because it's a vector, it needs to point somewhere. You can ask, where is it going to point inside the soliton? It's coherent throughout this region. One thing, it could be linearly polarized, so it's just oscillating like this, up and down. Or it could be circularly polarized, like this. This configuration ends up having, that looks like this, ends up having 0 spin angular momentum, whereas this configuration now has maximal spin angular momentum, which is h bar times the number of particles in the system. So think about a macroscopic object like this, gigantic size, astrophysical in size, with a huge number of quanta, 10 to the 83, 10 to the 23, depending on the mass, and it's h bar times that number. That's the spin of these objects. So it's really a gigantic microscopic spinning object. So I think that's something that's worth looking into in the future. Yeah. Good. So in a parametric way, the size of the solitons is typically the de Broglie scale in the system. So it's 1 over mv, where v is the velocity dispersion of this system in which it is born. So for v, for our galaxy, is 10 to the minus 3c. And then depending on the mass you pick, you will have a size. So for example, for a 10 to the minus 22 EV, it's about a kiloparsec. For 10 to the minus 19 EV, it's about a parsec in size. And depending on the mass that you pick and an environment in which it is born, it'll be of different sizes. Yes? That's right.
Because you have a Bose-Einstein condensate, what I was wondering is whether Bose-Einstein condensate property is rho
Okay, that's a great question. So the Kibble mechanism typically was talking about producing cosmic strings. So there were, or vortices in the language of BECs, right? So that was more talking about topological solitons. So different regions, the field had different phase, and then when you wrapped around it, you would have something where you couldn't decide where it would be, and it would create a effective singularity in the middle, or a vortex. Right? So there you could imagine the properties breaking down for the system. In this case, there's no vortex here. Right? So you don't have to worry about that. You can write solutions here as well, which have vortices, and there you have to worry about this property, like both this non-relativistic approximation and the BEC aspects of this could be broken. But here, they don't seem to form naturally in the system. Okay. Yes? Okay, good. So for very light particles, so this is a little bit long answer. It depends upon the density of the environment. It depends upon the velocity dispersion in the environment, and it depends upon the mass. If you decide that the mass is the lightest allowed, let's say 10 to minus 22 eV, or not even 21 eV, sorry, or lower, and you create densities that are comparable to typical galaxies, then it can be roughly the age of the universe. But if you go to denser environments, that is early universe, they can form a lot faster. So it's hard to give a one number because it depends upon the environment. So different solitons can form in different places with different times. It depends on, and I can give you the formula afterwards about how it depends upon the density and the velocity dispersion. In the early universe, they can form a lot faster. In the late universe, usually if it's just gravitational things doing things, it takes a while to do it. Okay.
So the simulation that you showed with Flynn,
Yeah.
it's just right?
No baryons, yes. So the first one I showed you where I was doing a comparison between particle dark matter, and that was with baryons, right? So that was the one with that one does not have baryon. Yeah, just gravity. Yes. Yes.
Yeah, so if you want to observation look for, let's say, the cluster of predicting these things, like, is there a way to differentiate between, let's say, it's a CDM sub-zero or substructure, or it's a something?
I think yes. For example, this will create a chord region at the center of the galaxies or dwarf galaxies. In the CDM case, usually you expect a cusp. Again, I understand baryonic physics and things and so on. But at the very basic level, yes, it does create a difference in the structure towards the center. And the interference patterns also provide additional substructure that would not be in CDM. Here is a little bit about, I think let me start skipping through things because we have run through. This is spin density, starts out with almost zero, but as things cluster in the soliton, you see coherent spins all aligned together. Spin is not playing a role in the dynamics, it's just you're collecting density, and the soliton is a lowest energy configuration, and it's phase coherent, so you get spin density all lined up. And we see this all the time in the simulations. As many of you have noticed, I'm using some of the language from condensed matter physics, or rather BEC physics, and certainly some of these effects have already been seen for the scalar solitons, not with gravity, but with self-interactions. At Rice, for example, Randy Hewlett has been creating this in the lab and looking and colliding them, looking at what interactions they have. So it's quite great to see actually in real simulations what's going on. With Han Pu, we are now he's worked a lot on thinking about spinor BECs. So the things I'm talking with spin, there are analogs of that there as well. And we are thinking about trying to create how this can be done in the lab as well, to see their properties. I'm going to very quickly now skip this part. So I was going to talk a little bit about what happens in the GR regime with this, like strong field gravity, collapse to black holes, and so on. But I'm going to skip through this. So here's movies are okay, I think, still. So here's a collision of two of these guys and the gravitational wave signals that they generate in that case, and what you can learn from these things if they were observed. This is another very fascinating topic that I unfortunately don't have time for anymore, which is how these light fields are generated around spinning black holes. This is black hole superradiance. And even without spinning black holes, even around compact objects, you can have gravitational atoms forming. So there's a lot of interest in this area in trying to detect their effects around compact objects as well. And some people here have worked on it as well. Here is, if you do decide to couple these to light, when you collide them under the right parametric regime, you can actually get flashes of light from here as well. That would be something we could look for. And the light can be polarized depending on the theory that you are looking at. So that is something we can look for in the future. OK, so again, I really ran through this because I think I've taken too much of your time. So let me go ahead and summarize where we are. So the goal for me right now is to try to figure out what the mass and spin of this dark matter is. Obviously, I don't have an answer. We don't know it yet. However, what I have found is, for myself, is this period, or not period, this mass range where it's sufficiently light. There are many more interesting phenomenological implications on astrophysical scales that are worth probing. There's no guarantee, just because I like working on it, that dark matter will be there, but it's fun, so I keep working on it. And in this domain, in this light dark matter region, I've told you about some interesting phenomenology associated with interference, the solitons and their implications, as well as growth of structure. I hope you found this interesting. Let me end by just acknowledging the group at Rice. I share a group with Professor Andrew Long here. I apologize that this picture is a year old. Some of these people have moved on and new people have come in, but gives you a sense of who these people are here. If you want to know more about Rice, so we have as I've been talking with the faculty here, there are MOUs that have been exchanged with Rice. If you're interested in learning more about what's happening at Rice, please let me know. And if you want to know where we are, this is our cosmic address. And unlike dark matter, we are easier to find. Okay. All right. Thank you. Yeah.
This density profile for the scalar and the vector.
Yeah.
It shows that it's a four-line profile, but in one case there is another extra length scale apart from the four length.
So I think this is a great question, good observation. So the core part of it is basically there's a soliton there. And when you see a deflection from that, you're going from the soliton to an NFW-like halo. So whenever your length scale becomes large compared to a de Broglie scale, then you don't know whether it's what type of particle it is. It's just a particle. You can think of it as particle dark matter, so you join into an NFW halo. The soliton size is roughly the de Broglie size. And beyond that, it just joins with NFW halo. So the break is at the de Broglie scale, roughly. Now you saw, what you observed was one of them seemed smoother, and one of them seemed a little bit sharp transition. The sharp transition is for scalars. For vectors, the transition becomes smooth because now you have three fields, and they don't always directly sit on top of each other. So they smooth out this break. So it's the same break, but it's just smoothed out. But good observation there. Yes? Yes. Yeah. So the simple answer is no at the moment. There have been people who have been writing papers based on some of the LIGO events that are not so easy to describe based on neutron stars and black holes. And there have been claims that they are better described by some aspects of these boson stars that I've talked about. But I think it's a bit premature, in my view, to say that we have actually seen these guys. It's just, as we collect more data, I mean, we are obviously going to see some things that don't exactly match expectations. But I would, as always, right, if there's a simpler conventional explanation, we should go for that first before jumping to something more exotic here. Not to say that we shouldn't look for them. People are creating templates to see them, but the data quality is not good enough yet for me to say that the fact that we are seeing deviations from what we had expected means that this is the answer. It's just saying we are seeing deviations from what we had expected so far. Yeah, so if you see it, then you will get something about the mass of the boson, right? So you will get effects on the constraints on the mass of the boson. The degeneracy will be with how compact it can get. But usually, that's not, to see any gravitational wave signal, it basically has to be as compact as it can be. So that roughly scales out. And then all that remains is what is the mass of the boson there. Okay. So you would learn something about the mass from there, if you actually believe the detection. And the case that has been used is what is called a Procas star. So it's a vector star, but the ones that people, before some of our work, what people were looking at Procas stars, they were looking at hedgehogs, meaning the vector field was all pointing usually outwards, right? Not in all cases, but in many cases. But that turns out to be not the lowest energy configuration. The ones I was showing is actually a lower energy configuration, so more likely to be found. But people have now, of course, done both and tried to see that. Yes, please. Yeah. So very good question. If you are talking about, so we already know that way before matter radiation equality, dark matter better be significantly non-relativistic. Otherwise, it can't be good dark matter candidate. So even by, none of these simulations that I have showed you today were before matter radiation equality. So we already know that this is good at that level, right, from then onwards. When you go way into radiation era, when these fields were produced, yes, they would be relativistic. But so you want to start with relativistic simulations, and we do. Right? So in many cases, when we're thinking about production of these things, we do relativistic simulations, which I didn't have a chance to talk about at all. But then as the universe expands, even if you started out with relativistic things, the expansion will make it non-relativistic. And at some point, you want to patch up those relativistic simulations, then do some WKB approximation, because you can't really do relativistic simulations for too long, and then eventually take those results and patch it to these non-relativistic simulations. What I said is easily said, but you have to be a little bit careful in doing that, and it's not always done. Usually people just assume the late universe, these are the initial conditions, and move forward. But we are trying to do this whole story. And I can tell you how it works in the early universe in more detail, if you want. It's a good question. You certainly, for production at early times, you have to take relativist, you solve the Klein-Gordon equation rather than the Schrodinger-Poisson system. You basically use Einstein's gravity and Klein-Gordon together, or Procas equation and Klein-Gordon and Einstein's gravity to actually do this. Yes. Oh, sorry. So very good question. So solitons usually, which are held together by gravity, can have lifetimes comparable to the age of the universe. But if the solitons are held together by self-interactions, then the lifetime will be reduced. So think about self-interactions, for example, in a scalar field theory. It's m squared phi squared, let's say self-interaction is lambda phi 4, right? Attractive interaction. Then that is attractive interaction that's holding you together against dispersion. But that same attractive interaction is also providing a channel for these particles, many particles to come together and decay, right? Because it's not a free field. So generically, you will find that it will reduce the lifetime. If you try to calculate the lifetime based on Feynman diagrammatics, you will get a completely wrong answer. You will find that it decays very quickly. But if you actually do a slightly more careful calculation, in fact, a classical calculation, you will find that the configuration lasts surprisingly long, even with self-interactions. It's related to the fact, as I was telling some of you, that the solitons are wide compared to the wavelength at which they want to radiate. So they're terrible antennas, right? So they can't radiate effectively. So that's why they end up being stable. So it's a configuration that's stable because they're somewhat broad compared to the microscopic length and time scales. Okay. But there's a lot of literature now on understanding the stability of these objects, but still a lot more to be done, because most of these things are done classically. Quantum mechanically, the stability is slightly different because you always have some fluctuations you can couple to just from uncertainty principle so quantum mechanically, usually your lifetimes are lower than your classical ones, but the quantum mechanical calculation without taking into account the actual many-body configuration would also be completely wrong. So you have to do it carefully using both this profile, that is, you are doing quantum mechanics, and spatio-temporally varying background. And then you could get the right answer.
So we don't have
Yes, so the calculations that are done for, there's a classical lifetime that you can calculate, which is just classical physics that you can get. The calculation for quantum mechanics that is done is perturbative, but takes into account that the thing you are perturbing around is a spatial and temporally varying background. So it's still perturbative calculation, but takes into account the spatio-temporally varying profile that you have. But that's at an early stage. I mean, not many people have done a very careful calculation of that. It's a tricky one to get it right.
So the simulation that you showed comparison of the gas and the
Yeah.
I just want to understand it's more like, is it transfer of relatively low redshift case, and how exactly the gas and star distribution come here? Is it from the first principle, or is it like using some sort of recipe of the dark matter mass to the gas mass and stellar mass?
Good. So I can't comment in complete detail because we'll have to, but I can point you to this paper by Anastasia Fialkov and Motz, where they have the description of but it's not just painting things on. There is hydrodynamics in the code already. So we are not just taking the dark matter distribution and adding it on. Plus, this is more, we can't get to very low redshifts here. This is actually high redshifts that the simulations are working in. I forget what the number is. We can't get to redshift of 0 with these.
There are already stars.
Yeah, they're already stars. Yeah, yeah.
In terms of whether one can look at these two scenarios when at a much earlier time and think in terms of whether the bias parameter between the baryon and the dark matter distribution will be significantly different between these two, because that will have significant implication for the 21st.
That's true. So certainly, I think people have thought a little bit about this. They're in the quasi-linear regime, roughly. The key thing they look at is that for this wave-like dark matter, it's not so much the bias part, but the wave-like dark matter usually has a cutoff in the power spectrum. So there's a lack of power on small scales compared to the CDM case. And that can be a distinguishing feature, even at early times, right, in terms of how much structure is there on those small scales. And that's what people have been using. I think even, I believe 21 centimeter, as well as people have used Lyman alpha and so on later times to put constraints on that. So we haven't, of course, detected it, but we've tried to put constraints on the mass, predictions for this.
Okay, now let's thank Mustafa.
All right. Thank you so much, everyone. Appreciate it. Thank you. Thank you.